Okay, thanks, Motez. Hello everyone. Thanks for joining us at the FreeFlyer Users Conference. I'll be wrapping up the day in the conference talking about some tips and tricks to keep in mind when performing large-scale constellation analysis in FreeFlyer. First, an agenda for the upcoming presentation. First, we're going to talk briefly about some of the types of large-scale analyses that you can perform with FreeFlyer. And then we'll move on to an example of a mega-constellation analysis that's actually provided with FreeFlyer as a sample mission plan. Next, we'll divide the analysis tips and tricks into 3 sections. We're going to be talking about modeling and setup for large-scale analysis, how to implement capabilities in your mission plan for these large-scale analyses, and then finally, how to execute your mission plans for efficient analysis. Then we'll conclude and take questions. Just a reminder that all attendees are going to remain muted throughout the presentation, so if you have a question, go ahead and use the Ask a Question functionality in the GoToWebinar dashboard. They're going to be sent to our moderators and we'll answer them at the end of the presentation. So what types of analyses can you perform on large scales in FreeFlyer? Today, we're going to be focusing on analyses that require the propagation of a large number of spacecraft states and either the interaction between those states or the geometric relationship of those states with other objects such as ground stations, ground vehicles, or regions on the Earth's surface for coverage. Specifically, 2 examples. The first one for mega-constellations with member numbers in the hundreds or thousands. You can perform lifetime analyses to see when your orbits decay, or region coverage maps to determine what percentage of area on the surface of an Earth is covered by constellation sensors, or you can do chain link visibility between ground stations and cluster members, and then to other, either satellites or ground stations and other ground vehicles. So you can also perform large Monte Carlo runs in FreeFlyer. So you could use this for a debris field propagation to see the orbit evolution, or maybe a conjunction assessment between many states of a spacecraft, which are sort of representative of a covariance around the spacecraft, or even Monte Carlo trajectory design. Today, we're going to be focusing on the large constellation analysis for this presentation. So take, for example, this sample mission plan. It's a mega-constellation region coverage mission plan that's included with your installed FreeFlyer. In it, we're propagating a large constellation. It's user-defined. You can put as many spacecraft as you want and choose how to visualize those. Then we perform region coverage between each of the spacecraft based on their sensors, what they can see on the ground, these different regions. In this case, it's the continental US. And then it also computes chain visibility between 2 ground stations in the US, and then any of the constellation members that are, with access to those 2 ground stations. And then it's going to visualize that in 2D and 3D, output some statistics to the view windows as well. And it's doing this all simultaneously. So if you start increasing the number of points in the point group, or the number of spacecraft in the constellation, you're going to start running into slowdowns, especially if you're also doing the 2D and 3D visualizations. So where can we derive some of these efficiencies? Well, we can pre-compute some of the orbits to take away the overhead computational load of propagating the spacecraft simultaneously doing contact analysis. And then we can be intelligent about what spacecraft we select to do contact analysis. You don't want to be taking a spacecraft on the other end of the globe to try and see if it has contact to either the ground station or the region. And then we can also tune some of the force modeling to maybe do a lower fidelity lifetime analysis, not using the highest order integrator, or all of the gravitational influences of all the solar system objects. We'll discuss all these methods in the following slides, though. So first, we're going to talk about the modeling aspect, what you can tune in your initial model to get these efficiencies for constellation analysis. When choosing initial states for your constellation, we recommend utilizing mean element sets such as the J2 Brouwer Lyddane for calculations of orbital parameters such as spacecraft period or spacecraft height. The BLJ2 element set they account for realistic perturbations to the Earth's gravity model, and they're constructed based on an average over time. So the default Keplerian elements are oscillating, meaning they're purely instantaneous values. They treat the orbit as a classical two-body system in which they assume that the central body is a point mass. And we recognize that just using the BLJ2 elements themselves aren't going to get you a perfectly stable orbit, but they're better to use than the oscillating elements when you're targeting something such as SMA in a targeting loop for your stability maneuvers, especially when you're targeting stability between planes. So you'll see the plot on the right, which is a plot of semi-major axis as a function of mean and true anomaly. And you can see how the semi-major axis varies with the Keplerian elements by about plus or minus 9 kilometers. But note, it remains fairly stable for the BLJ2 element set. So, when you're targeting a specific parameter in your targeting loops, it's best to use those BLJ2 elements to create that stable orbit. Next up is the fidelity of your force model. So you can tune the fidelity of this force model to achieve both the required accuracy, but also maintain a reasonable computational speed for analysis, especially when you're changing a lot of things on the fly. Consider using a less accurate integrator for your lifetime analysis or orbital decay models. Integrators such as the Buller-Stower or Cowell integrators, they're not as accurate as RK89, which is the default in FreeFlyer, but can be 70 to 80% faster and sufficiently accurate when performing these lifetime analyses. You can see the image right here on the right is from the FreeFlyer help file, and it can help you choose an integrator that works well for whatever analysis you're trying to perform. So if we take, for example, a dense Walker constellation, maybe if you're trying to get just a snapshot of the region coverage, so how many planes you need to get full coverage based on your sensor sizes, and you're not so invested in either a coverage revisit statistic or specific outage areas, you just want like kind of a snapshot, you can use a two-body integrator to get an instantaneous look at that coverage of the constellation. Also consider planetary bodies you're modeling. By default, a spacecraft's force model is considering Earth through a geopotential file, which is definable, and then the Sun and Moon as point masses. If you're analyzing a Leo constellation, you might only consider modeling Earth's gravity. You might not need the Sun and Moon potential files. And then you can also change your analysis step size. So you can change it to a variable step size instead of a fixed integration step size if you're doing those long-term simulations. So for output efficiency, when viewing large constellations in the 3D view window, it's less computationally taxing to represent the constellation as a group, not 3D models with the tails drawn. You can see in this graphic on the right here how much smoother the animation is when viewing as a group, as opposed to drawing all the 3D models with all their tail histories. And to reduce memory usage, plot data is thinned after a predefined number of data points are plotted. It's called data culling. The user can increase or decrease the number of points to plot before the culling happens. Maybe you just need to see a general trend of the value as opposed to the exact value of that parameter at each time step. So you can, cull more if you're just trying to get that trend line. It'll help speed up your mission plan execution, especially if you're outputting all this to an output workspace. FreeFlyer also gives the user the ability to perform batch updates to plot windows, to view windows, to data tables and grid windows. So you can perform updates at a single instance in time, as opposed to doing it every time you're stepping your spacecraft through its propagation. It'll further decrease the runtime and computational overhead if you do those batch updates. So we recommend pre-computing orbits and reading from an ephemeris if you can for an analysis that changes investigated parameters frequently. For example, if you're varying the threshold for a conjunction assessment analysis for your constellation, propagating via an ephemeris file it's going to allow you to change the CA threshold, through multiple engineering cycles, while not devoting computational resources to repropagating all the spacecraft themselves. So this ensures that you're starting from the same baseline and working through the exact same mission sequence each time you repeat the cycle. You want to redo the analysis, not the entire scenario. And if possible, use a binary ephemeris file, such as a SPICE SPK. Their file sizes are much smaller than their ASCII equivalent, and the read and write times are much faster. And in FreeFlyer, we actually allow the user the ability to read from a SPICE file and also write out to a SPICE file. So moving on to implementation of your mission plan and how to get efficiencies from that. So when you go into the script itself, be sure to, FreeFlyer allows you to define lists of objects, such as lists of spacecrafts or ground stations or ground vehicles or vectors. So creating a list allows you to interact with and manipulate with a large group of objects by indexing through them and using a loop. A formation object specifically is a list of spacecraft. It's just built into FreeFlyer. And by using a formation object, you can step every spacecraft with a single step command, and it allows for simpler and more concise script. You can see this graphic on the right here shows how easy it is to create a formation, and then it manipulates a property, in this case the true anomaly, through a for loop. And then we're going to propagate that entire formation and then update it and view it all in a couple lines, just 12 lines of code. Note that you can also import your entire formation of objects through a TLE file. So instead of defining each of the Keplerian elements or Cartesian elements, you can just import it using our load TLE functionality in FreeFlyer and have your formation based on a single file. Moving on, so FreeFlyer allows the user to define a collection of related FreeFlyer objects for easy code organization using structs. Michael Volley mentioned this. This is what he built his parallelization on, using structs and JSON data. So once a struct is created, you can conveniently pass data between processes and easily read and write those JSON data files. So you can see an example of a JSON data file over here on the right, which you would ingest natively into FreeFlyer. And using a structure such as this when defining input and data and output data, it allows you to recreate an analysis scenario with different data without having to either reparse a new file type or redo a portion of your code. It's just pulling from the same data file, so it's easy to manipulate parameters without manipulating your code. FreeFlyer also I mentioned that they allow the use of JSON data files, which is supported across most common programming languages. And then this will lead to the eventual transition and automation from the FreeFlyer GUI and IDE script to a driver code such as Python, Java, or C++. Be sure to modularize your code. This allows for easy parsing and debugging. Separate freeform should be used for either setting up variables or setting up view windows, parsing data into objects, and then you have your propagation and analysis loops. You can use block statements to group and easily collapse code snippets for easier parsing. You can see that in the GIF on the right here. Once you're more familiar with objects and methods and commands in FreeFlyer, try to create everything in script as opposed to the object browser. The script gives the user the ability to modify more parameters in the object browser, and it makes parsing through your mission plan a lot easier when using the find or find all text functionality, especially through your mission overview. You're also able to copy, paste, and modify freeform script and move it around freely in the freeform script segments. Next, use procedures for portions of code that often get reused. This could be either setting up a propagator for a bunch of different spacecraft, or adding thrusters to all your spacecraft, or doing some kind of calculations analyses. The procedures can be defined in the mission plan itself. You can put that in its own free form where you define your procedures, or you can put it in an external procedure file, a .ff procedure, and then you can use that across multiple mission plans. So you can, recycle how you set up your spacecraft, or make plots or something like that. And then use the profiler to see how efficient your code is executing. So FreeFlyer comes with a profiler that will show where the bottlenecks in your mission sequence are. You can call the profiler with the syntax above. It's just through the command line. And what it's going to do, it's going to execute FreeFlyer.exe, and it's going to create a lines file and a scopes file. You can see examples of both of them below here. The scopes file, it's going to list any information about the execution time of the main scope, any procedures, and macros that are included in the mission plan. In the scopes file, you can see there's an exclusives column. So that exclusives only includes time spent executing the lines in the current scope, not executing sub procedures. But the inclusives does include the execution of scope and subscopes called by the sub procedures and macros. And then the final column is hits. So that's how many times that procedure was called. And then the lines file, it contains the duration and sections each actual individual line of your code is called. So when you're going through your freeform script, it's going line by line with that. It's going to report the number of hits to that line. It's going to give you a little script snippet of what you actually typed in your freeform. And then it's going to tell you the line in your mission overview. So you can go directly to that line to see, all right, what's going on here? Why is it hitting so many times? As well as the column, and then what scope that line is hit. And this allows for easy debugging. It'll show you exactly where your bottlenecks are going to be in your mission plan. Maybe something shouldn't be hit so many times that that that's a good way to say, I need to go this line to figure out what's going on. So finally, we'll talk about mission plan execution. This builds off what Michael Volley and Stefan did, or what they talked about. This is how we set up that scenario for transition from FreeFlyer to the cloud. So where you'll find a lot of efficiency is using the runtime API and multiple FreeFlyer application instances. A standard FreeFlyer license will allow the user 6 simultaneous applications of FreeFlyer, which can be run, so you can have the same mission plan run on multiple sets of test data at the same time. For instance, for a constellation of, say, 360 spacecraft, you could propagate 60 spacecraft at a time across 6 instances of FreeFlyer, all simultaneously, and then combine those results back. FreeFlyer, I think Stefan did mention this, but FreeFlyer licensing supports up to an unlimited number of simultaneous instances. So we have a HPC licensing scheme. You can contact sales if you want to do a big cluster HPC license like that. But if you note the graphic on the right, it's showing the same data being run by one instance of the FreeFlyer runtime API versus another being distributed to 6 FreeFlyer instances that execute simultaneously. You can see the difference in the runtime, and that's really gonna it'll really add up if you're doing a lot of analyses, a lot of different mission plans. Just to talk quickly about the runtime API, it's a headless version of FreeFlyer, or the FreeFlyer Astrodynamics engine, that can be used to call your predefined mission plans and launch through a C, C++, C#, Java, Python, or MATLAB interface. So using one of these interfaces and the runtime API's asynchronous programming, you can create processes which will launch multiple FreeFlyer application instances and distribute the workload across multiple CPU cores. It's available for both Windows and Linux, and it supports visualization. So finally, build for Parallelization. This is kind of how our workflow went when we started with Michael Volley's initial FreeFlyer application. He built out his analysis in the FreeFlyer GUI. We then wanted to transition some of that to the cloud. So Stefan took some of that and put it up on AWS. So be sure to build out your analysis from the beginning to be parallelized. So we start on the left, where we start with a simple standalone FreeFlyer mission plan. It performs a specific function, in this case, ephemeris generation. You want to be sure to just do one function at a time. So you don't want to be doing ephem gen and maneuver planning at the same time. If you start to combine those capabilities, it's going to be harder to parallelize down the road. You want to break the problem into the smallest bits possible and efficiently distribute those across your compute resources. But in the very far left, you're just executing FreeFlyer as many people do through the GUI, and then getting an output, a JSON output. So after we've created those mission plans, the single ones that do a single process ephem gen in this case, we're going to then move to calling FreeFlyer or ff.exe through the command line. So it's still going to be FreeFlyer GUI driven, but you're going to be able to use multiple JSON data sets using a driver such as a batch file. And then through FreeFlyer, you're going to be able to call the ff.exe engine to run those multiple JSON data sets in parallel, all within FreeFlyer itself. The command line, it still just calls FreeFlyer to execute. There's no memory management or explicit distribution of processes to computational cores. Where you're going to get that power is going to the runtime API, using that within an embedded primary system automation. So you can build that in C++ or Python. Stefan did it in AWS. So that's going to be managing all of your resources, all the different calls, and it's going to be utilizing the FreeFlyer runtime API to do those in parallel. So to conclude, be sure to use a mean element set such as the BLJ2 mean element set when targeting orbital parameters for stability when you're targeting those SMAs. Targeting an oscillating Keplerian element may not converge or reach the desired end target. Modularize your code by breaking the freeform script into distinct portions that perform specific functions. Be sure to use those lists and those structs when possible and pass data using JSON. And build for parallelization from the start. So think about how a mission plan can be broken up into easily distributable pieces and simplify the scope of those mission plans. And once you've built that mission plan to be parallelizable, use the runtime API. Distribute those FreeFlyer instances across computational resources. You can do that either locally, or then you can move that to a cloud setting. To save on computational load, you can pre-compute orbits and then use a binary ephemeris if possible to read those ephems. And then finally, use the profiler to determine where the bottlenecks in your mission plan are. It's a really good resource for debugging and seeing what's holding up your mission plan and how you can fix it. And that's all I have. I'd be happy to take any questions.
Team, which would be happy to assist. Right now we have a few questions and they're just they're enough for the time that we have. But if anybody has more questions, let us know. The technical support team is on the line and we'll be able to follow up with you. These questions are directed to the technical support team, but feel free to pitch in. We already have some feedback, so I'll read the questions and I'll also relay the answers that our tech support team has prepared. So the first one is, how does SPK relate to standard ephemeris with respect to prediction accuracy? Are there any caveats to using that format? And to that, I would say it's just as accurate as regular ephem. The only caveats for the SPK file is that the file must be in the BSP file format since it's binary, and regular ephems are in ASCII. So there's not really anything else to that. Next question is, so given on day 2 the presentation optimization and today's presentation, is it possible to define constraints such as 25 spacecraft launched at a time on a dedicated orbit with certain parameters, and basically try to optimize that in FreeFlyer. And to that, I would say, so yes, the scripting interface gives you the flexibility to customize your optimizations, problems, constraints, and objectives functions however you like. And we'll be able to follow up with you on that and provide you with a sample mission plan and answer that in more detail and help you set it up. Another question that we have is there a module to optimize the constellation parameters given some range or altitude eccentricity? So FreeFlyer doesn't have any modules, as we mentioned, I believe on day one during Michael's presentation. We have two tiers, the engineer and the mission. The mission has all of the capabilities with the optimization included. And yes, you can do that in FreeFlyer. You can specify the parameters, and it's well explained in the optimization section in the help file. And as you start to implement this, we're going to have our team supporting you as well. We have more questions coming in. So is there integration of Git in the code interface? Mark, do you know? Let me go to that if you don't mind.
Yeah, it's not integrated into FreeFlyer. You can use like a C# extension to use Git in FreeFlyer apparently. But if you want to, you can also use other resources to manage your your scripts and upload it to like Confluence or something, or track it that way, track changes. But yeah, it's not built natively into FreeFlyer.
Yeah, you're spot on here. And the tech support team would add and say that the mission plans are stored as XML files, and all FreeFlyer script is stored in C data blocks, which makes it easy to see differences in a Git interface. So there's not currently a built-in Git integration, but we're tracking a ticket to add that functionality. And the last question for today is, how many licenses do you estimate is required for a team of FDS engineers to operate a fleet of less than 50 spacecraft, in addition to the network licenses shared by the concurrent AWS instances? That question, as we're all aware, it has many variables, and it depends on how you configure up your operations. I would say it will probably be single-digit number of FreeFlyer licenses, I'm fairly certain, and you can drop it to perhaps 5 licenses, give or take, depending on how you set up your operations environment. But that's really something that we would need to talk about in more detail. What do you think about that, Mark?
Yeah, there are definitely a lot of different variables. It really depends on what your cadence of operations is going to be. It depends on what your mission requirements are. So I would say follow up with us further. There's a specific use case that we can flesh out with you. I think it's easier to talk offline about that.
Absolutely, yeah, and we have experience in setting up the optimal number of licenses and license types, because we have certain license structures that are dedicated for constellations.